Hello and welcome to this session. The purpose of this video is to take a thorough walk through the steel beam module in the structural engineering library, and it will be a thorough look at the modules, so the video overall will be quite lengthy, but we will set up the table of contents in the most modular way that we can so that the topics are accessible in smaller increments and of a topical nature. You can just use the table of contents to navigate to the point of interest. So with that, I have started a brand new project file called Sample Steel Beam, and what I'll do is click on the calculations item in the project manager and then choose Add, and I'll use that to add a steel beam calculation to this project file. Now we can see the user interface for the steel beam module. And what we'll do is first just take a quick walk around what we see as a general layout on the beam module. Starting up at the top of the screen, we see a graphical depiction of a beam. We see some tools that we can use to modify the model and to create the exact beam model that we want to analyze and design. So we'll come back to that shortly, and I'll demonstrate how we can actually configure our specific beam. The next section down is this section toward the middle of the screen that includes some tabs. This is generally the data input panel, so we'll kind of use the beam graphic and its tools as well as this data input area hand in hand to construct the model and establish all the parameters and settings that we want the analysis and design to consider. And then that will lead us to this third portion of the screen, which is generally where results are displayed. So after we have everything configured and ready to take a look at final results, we'll move down to this lower portion of the screen where we can look at a variety of different sets and subsets of results. And this will also be a portion of the video, so we'll work our way through each of the different options for viewing results and briefly explain what all of these different types of results mean. The last thing that I'd like to point out is down at the extreme bottom of the screen, and this is the area that we refer to as the status bar. Right now it just indicates recalc complete, and then at the right hand side it indicates my current build number. I just like to point that out because there are times during the modeling, analysis, and design process where the program will be communicating with the user some sort of information, like for example it may be telling us that we don't have any section selected, or it may be telling us that we don't have any load combinations set to run, or those kinds of things. And so it's very important to get in the habit of glancing down at that lowest line on the screen and occasionally just checking to make sure that the program isn't blinking a message at us to tell us that it's having some difficulty or needs something from us. Okay, with that basic introduction, I think the next thing that we'll do is we'll work our way back up to the diagram of the beam at the top of the screen, and we'll start to use these controls to establish the model that we actually want to analyze and design. Now what I have in mind for this sample is a beam with two supports. We'll use a 24-foot span, and then I'd like to provide a 6-foot long cantilever on each end of the beam. So now I'll show you how you can use these controls and some of the information in the tabs to establish that model for the beam. The first thing that I'll do is just point out that there are some instructions in this blue band right beneath the beam graphic. They say to click on the plus and minus icons to add or delete spans. This message indicates that we can click on a particular span to select it. Right now I'd point out that we only have one span, so it's selected by default, but when we create a multi-span beam we'll see that the selected span appears in yellow. And then the message over to the right says click on a support to modify it. And if I hover over a support, I can see that it appears as a little icon, and we get a little pop-up help text that tells us what kind of support we currently have. So what I'd like to do first is I'd like to show you how you can add a cantilever at the left end. What I'll do is use the plus and minus icon at the left, and I'll click that, and up comes the select add or delete dialog. Well, in this case, it doesn't give us the option to delete because we already only have a single span and we can't have less than one span in the model, so it knows that we must want to add a beam, and in fact that's what I want to do. I'd also point out that down here in the category called for the new span, it gives us some options to use the current span length and bracing values, to use the current beam size and properties, and to use the currently assigned loads. So these are user options. You can select or deselect these as you see fit. I'll just leave them selected by default because I find it easier to come back in and modify those on a span-by-span basis afterwards. So now all I need to do is just click the OK button. And what we just did was we added a span to the left of the original span. So this is the new span and it's highlighted in yellow. Now, I said that we wanted to create a cantilever. Notice that it came in with a pin support. So in order to make it a free end or a cantilever, I'll just hover over that pin support at the extreme left and click that icon. And then from the little pop-up list, I'll choose free end. And now we can see that the graphic changes to represent a free or unsupported end. Now the span length needs to be changed because I said that I wanted to make a 6-foot long cantilever. There is no way to actually modify the span length from this little graphic, but instead what I'll do is come down to the Beam Span Data tab, and when I click that, I want to point out right away that there is a Select Span control, and it offers as many buttons, numbered buttons, as there are spans defined in the current graphic. So it is the span number 1 that I want to modify the length of. And instead of 10 feet, what I'd like to do is change it to 6. So while the 10 feet is highlighted, I'll just edit the 10 to 6. And then I'll use the spin arrows to toggle up 1 click and back down. That's just a convenient way to register the new value in the system. And now it updates to show us that the cantilever length is 6 feet as specified. Now while we're here, I also mentioned that I'd like for the center span to be 24 feet long. So I'll choose span number 2. Notice that the 10-foot long span becomes the yellow highlighted span now to indicate that the focus is on that span. And instead of 10 feet here in the span length, I'll key in a value of 24 and then toggle up and back down to register that value. So now we have a 6-foot cantilever at the left and a 24-foot center span. We need to make that the center span by adding the cantilever at the right. So what I'll do is come over to the plus and minus button on the right hand side of the graphic and give that a click. Now we can see that we have the option to either add a beam or delete a beam, and specifically it would delete the beam that's to the left of the support that I just clicked near. Well, we don't want to delete the 24-foot span, we definitely want to add a new beam, so I'll just click OK. And notice that it adopts that span length, that beam size, and the support conditions, and if I had loads on the model it would adopt those loads as well. But now we know that we can quickly change this, so I'll point to the pin support at the right, click that, and choose free to make it into a cantilever. And then while I'm here on the Beam Span Data tab, I'll make sure that the focus is on that third span. And instead of 24 feet, I want to revise it back down to 6 feet, so I'll key in 6 and toggle up and back down. Okay, so at this point, we have created the physical model that we're after for this exercise. 6-foot cantilevers at each end and a 24-foot center span. At this point, what we'll do is move back to the General Data tab so that we can start a progression through each of the subsequent tabs, generally in order, and talk about them specifically in that order. So here on the General tab we see that we have a description. I can just overwrite the default none value with something like sample. for instance. Or this could be whatever text is meaningful to you to distinguish this beam from any of the others in your project file. Notice that over on the right we have an option for the design method, so we can choose to either do ASD or LRFD. I'll choose ASD for this example. And then in the design values category, notice that we can provide the FY value for the yield strength of the steel. There's also an icon right here that displays a yield stress database, so if you're not familiar with exactly which values are available for the various types of steel sections, this is coming right out of AISC, and you can choose any of the values and make them the value that's populated in the input field. So since I intend to use a wide flange shape, I'll choose the most common value, which is going to be grade 50, and then I'll choose select, and that just populates that value with that choice. The other value is Young's modulus, and 29,000 KSI is correct for steel, so I'll leave that alone. Back over here on the left we have a beam material selector. That allows us to toggle between the various materials that are available for the beam module itself. Now the focus of this example or this video is the steel beam, so I'll leave it set to steel, but just notice that if for some reason you decided that you had started as steel but wanted to change it to one of the other materials, you can just toggle to the other material. The none option is the one that will bring you to the general beam analysis module, where it's not material specific, but you just enter the properties for the stiffness, and it doesn't actually perform a design, it just performs an analysis and provides results. The category named compression edge lateral bracing is one that warrants a little discussion. This is referring to our lateral bracing for the beam, and we have some options like the compression side is fully braced or the compression side is completely unbraced. Those are relatively obvious. The only thing that I'd like to mention with this category and the settings in general is notice that it does not refer to the top or bottom flange, but instead it refers to the compression edge. So in the present version of Structural Engineering Library, it interprets these settings to be applicable wherever the member is in compression. Naturally, in a member like we've defined here, that can mean that there are compression locations in the top flange in some areas and compression zones in the bottom flange in other areas. So whatever we set in this compression edge lateral bracing category will be interpreted as being applicable wherever the member experiences flexural compression. Okay, the other two options are to set a uniform spacing for bracing, in which case I can establish where the brace points start and then what their spacing is on center. And those, I would point out, are always referenced from the leftmost end of span number 1. Even in a situation like this where there is no true support at the left end, this value is interpreted as starting at that leftmost end of span 1. And then the other option that I have is called define bracing span by span. If I choose this, then we get a little message that tells us that since this becomes a span specific piece of information, we now would need to move over to the beam span data tab to provide that information. That's a great segue for us to move over to the beam span data tab in just a moment. I'd just like to point out that there are a couple other options that are tucked into this compression edge lateral bracing category. One of them is an option, if you see fit, to use inflection points as brace points. That option is available that you can select. And the other option that's somewhat related here is an option to force the value of CB to a constant value of 1 for the entire beam. So that option is here for your use as well. So with that, I'll make a segue over to the beam span data tab. Now on the beam span data tab, I'd just like to start out by coming directly to this compression edge bracing for selected span category, because that's sort of what relayed us over to this tab in the first place. And this is the way that you can define unique bracing for the various spans that you have defined in your model. So this is somewhat of a continuation of the conversation we had on the general data tab regarding compression edge lateral bracing, except that if you choose to define it on a span by span basis, just want to point out that that is done here in this category on the beam span data tab. So again, the options that you select here would be span specific. For instance, if I leave it set to, we'll say mid span for span 3, I can then toggle to span 2, and perhaps I say at third points in span 2, and then come to span 1 and say maybe it's at fifth points for whatever reason there. And then as I come back through the spans, we can see that it remembers and echoes the selection that I've made previously. The other options are to define a spacing where you can say that it starts at a specific location with respect to the left end of the named span and then occurs every so many feet, or there's also an option to define 3 non-uniformly spaced, perhaps, brace points with respect to the left end of the named span. So those are some options that are available here on the beam span data tab. The other thing that I'll mention is that on the beam span data tab we have a span length indicator. We used this span length indicator to set the span lengths for the 3 spans in this member, and it's important to know that this is where you come to set the span lengths in your model. The checkbox immediately beneath is called all spans minor axis bending. In other words, this is the way that we can indicate to the program that all spans are to be considered as bending about their weak axis, as opposed to the default, which is to assume that they're bending about their strong axis. Continuing down the left side here, this is where the program collects the deflection ratios for both the maximum allowable total deflection and for the maximum allowable live load deflection. We'll see those checks a little bit later on in the video, but these are the user inputs for the allowable ratios that it'll compare to determine whether the beam meets your design criteria or not. Coming over to the right hand side of the screen on the beam span data tab, we have an indication of the steel section name that has been selected. We can also see the steel section indicated up here under the individual spans themselves. And notice that there are buttons underneath the steel section name to indicate whether we want that section to be used consistently for all spans in the model, or if we'd like to vary the steel section on a span by span basis, we can choose this other button and say that we want to use the selected section only for the selected span. I'll leave it set to the use for all spans option, and now what I'll do is show you a couple different ways that you can choose the steel section of interest. One way is to use this quick list, where you can quickly select a section type and then choose the individual section that you want by single clicking in the list. Notice that it populates the steel section name here. It also echoes that steel section name for the spans up above in the graphic. And then if we just take a quick peek down in the results area, you'll also see that selected steel section indicated in the results area. So that is a way that you can use what we call the quick list. And the quick list is based on at present, the 13th edition AISC steel sections. Another option is to use this button, which accesses the full steel section database. So I'll click that button now. And I would mention that this is thoroughly covered in a separate video, so I won't spend a lot of time going through all the different controls, but I'll just choose AISC 13th edition. I'll choose a wide flange section, and then perhaps I want to scroll down to, say, a W10 by 22. I can choose that item in the list and say select, and now the steel section name reflects the W10 by 22. Don't be confused by the fact that you're still seeing a view of the quick list down here with a different section displayed in it, but the section that we've now chosen is definitely the W10 by 22 as echoed back up here on the graphic and as indicated down here in the results as well. The button that's just to the right of the steel section database is the member design button. That's a tool that we can use once we've applied loads and established our load combinations and all of our other settings to ask the program to automatically iterate through all of the members of a certain family and then indicate those sections that pass our specified design criteria. The other item that I'll point out while we're here on the beam span data tab is this properties tab in the background. This is a way to quickly take a look at section properties and geometric values for the selected steel section. So this is obviously a 10.2 inch deep member. That's for our W10 by 22, and these values are here for reference. I would also point out that if you have a specific need to, like for instance if you were trying to check a member that had some corrosion, there is the option to come in and edit the values, and as the note says, you're not actually making a change to the W10 by 22 in the AISC steel section database, but instead you're making a change to the properties that will be used for this calculation only. So you could theoretically come in and provide your own values for, say, area, moment of inertia, and section modulus to represent some flange loss due to corrosion. That might be one example of why you'd like to modify these values. So that was from this button called Edit Values. Okay, that's a thorough look at the beam span data tab. The next thing that we'll do is click the Span Loads tab. Now on the Span Loads tab, again I would point out that we have a Select Span control here where we can toggle between the various spans that are defined, and the reason for that is because the Span Loads tab is used to define loads that are span specific. So by default, when you define a load here on the Span Loads tab, it will apply to the selected span, but not to the other spans. What we can do, for instance, is come to span number 1, the cantilever at the left, and then we'll come down and we'll take a look at the tools that are available to define loads on this span. Notice that there's one line indicated here that says none for the load type, which corresponds to this selection right here. It's waiting for us to define a load with this item. So let's say that we want to provide a 1 kip load at the left end, the free end of this cantilever. What I can do is choose the point load type. That now changes this default load item to become a point load. It has a load source collection or data entry value, so I might say equipment just for our information, and then I can indicate the value or the magnitude of the point load that I want it to consider for each of the load categories. So perhaps it's a 1 kip dead load and a 1 kip live load. The location indicator is measured with respect to the left end of the named span. So if I want this to occur at the free end, then the value that I want in location is 0. So I'll leave that as is. And now we can see that there's a point load of 1 kip dead load, 1 kip live load at location 0 from the left span, and here we see an indication of the source that I entered as equipment and the load magnitudes again. If I had more loads to enter, I could use the Add Load button or Copy Load, and then I can edit and revise the load type, the load magnitude, the load extent, the location, and so on. Let's come over to span number 2, and I'll say that I want to change this default starting load from the none type to a full length load I won't enter a load source in this case, but let's just say that it's 0.2 kips per foot dead load and 0.2 kips per foot live load. Notice that there's a use trib width checkbox here when I use a uniformly distributed load. What this lets me do is change from the default assumption of a 1 foot trib width, in which case this is interpreted as a KSF times 1, which is equal to kips per foot. I could choose the use trib width checkbox and then indicate perhaps that it's spacing of 1 foot 4. So I could enter 1.33 and it would automatically take the KSF values that I've entered up here, multiply them by 1.33 and enter those resulting values in kips per foot down here. So it becomes a convenient way to enter a trib width other than 1 and let the machine automatically multiply out the magnitudes of the loads for you. The other thing that I should point out is that there are checkboxes to automatically include the beam weight or to not automatically include the beam weight as we see fit. And then the other option is an auto unbalanced live load placement option. This one will automatically take any live load that we've defined and skip load it in all of the possible permutations of applying to some spans and not others. This one is one to be careful with though, because it does extrapolate out to be quite a few different load combinations or permutations that need to be run, and so your computation time will increase noticeably, particularly on complex geometries where there are multiple spans. We'll leave both of those deselected for the time being. And the last thing I'd like to do is come over to span number 3, the span at the right, and I'd like to create a concentrated load of 1 kip dead load and 1 kip live load, and I'd like to make sure that that occurs at the right hand end of this span, the free end. Since the span is 6 feet long, I need to indicate a value of 6 for the location. So now we see that we have 1 kip dead, 1 kip live at 6 feet from the left hand end of span number 3. And that's exactly what I wanted to try to model on this beam as far as loads are concerned. The next thing that we'll do is take a look at the Loads All Spans tab. Loads All Spans is a way that we can apply loads referenced from the extreme left end of span number 1 in the beam system and have them potentially work their way across more than just that left-hand span. So for instance, if I wanted to indicate a partial uniform load that goes from midway along the length of span 1, which would be a value of 3 feet, and goes all the way to mid-span of span number 3, then I could say that would be a length of or an ending distance that would be 33 feet. I'm just adding 6 and 24 to get 30, and then 3 more to get 33. So I'll populate an end distance of 33, and then I'll provide a dead load of, we'll say, 1 kip per foot. If I quickly jump down to the sketch, I can show you that here's the graphical representation superimposed on the uniformly distributed load that's on span number 2. We can also see a uniformly distributed load that goes from midspan of span 1 all the way to midspan of span 3. So that's an option for the potential use for the Loads All Spans tab. Notice that it allows us to define loads that are full length uniform or partial length uniform. We can also define trapezoidal loads that vary linearly. A couple different options for defining those. So we can have some fairly complex load systems on the beams that we set up. We also have the option to create point loads or concentrated moments, and they can be repeating. So we have the option to indicate a starting location and then a spacing that they occur at thereafter, or we can choose this lowest option here, the last option in the list, to indicate that the specified magnitude of point load or moment is to apply to each span at the selected spacing, where we would use these buttons to indicate that they occur at the center, the third points, the quarter points, or at a specified distance from the left end of the span. So again, quite a bit of flexibility in terms of the way that we can choose to load our model. The next tab that we'll look at is Load Combinations tab. The Load Combinations tab currently displays a tab named ASD Service Combinations, and we can see that it represents what we would call service level combinations. This is a function of my having chosen the ASD design method back on the General Data tab. What we can do with the Load Combinations tab is choose a load combination set from one of those that is delivered with the program, or we can choose to create our own load combination set and select that for use for analysis and design. To demonstrate, what I'll do is click this button called Change Load Combination Set, so that instead of using combinations based on ASCE 705, I can choose from a list of load combinations, and perhaps I choose those from IBC 2009. Now the display updates to reflect the load factors for service level combinations as dictated by IBC 2009. Now this warrants a little more discussion because load combinations are complex, and in a lot of cases they vary depending upon the nature of the load, particularly when we get into the earth pressure loads. Sometimes the factors on those depend upon whether they tend to add or remove from the primary structural influence of the other loads. And so there may be reason for you to come in and modify certain factors. The other reason that you might want to modify factors is if you were working with some seismic loads and you wanted to try to build in a redundancy factor or a system overstrength factor. We don't have a direct way of implementing that at this point, but that's not to say that you couldn't come in and alter your load combinations to reflect the factor that you determine. So with that, I'd like to just point out that there's a little padlock icon here that serves the purpose of either locking the load combinations so that they are not editable, or opening them up or unlocking them such that you could come in and perhaps make some sort of a change like this, where I've changed the value from 1 to 0.6. And notice when I do make that change that the text description of the load combination reflects the factors that I've actually entered. So instead of 1H, it now reflects 0.6H. So just be aware of the fact that these values can be edited if you simply toggle the padlock icon. The adjacent checkbox is called Auto Minimize Combinations to Run. This one can be useful if you have a model where you only have certain gravity loads, and at the time you're not intending to run wind loads or seismic loads and so on. You can reduce the amount of work that's going on behind the scenes by making sure that Auto Minimize is selected, in which case it'll condense the amount of work that has to be done, and it'll condense the reports or the results displays so that it only reflects those load combinations that are actually being run because they contain non-zero loads, and it will eliminate those load combinations that don't come into play. The options down the side here allow us to make some modifications to the load combinations. For instance, we can choose to automatically create both the positive and the negative directions for load combinations that incorporate seismic. So if I was to toggle this check mark, or toggle this button on so that it displays the check mark, then in situations where this load combination or any seismic load combinations are generated, we would see not only the positive form of the seismic load, but also another combination would automatically be generated that would use the negative version of the the seismic load. Similarly, here is an option to do the same for wind. And then there's a button up here called Use Additional SDS Factors per ASCE, where we can enter some non-zero value for SDS. And when we do that, the program will automatically go in, and when we see these load combinations generated in other locations, they won't display this factor here, but we'll see it when we get to results. It will automatically include the additional component of dead load in the form of a factor in situations where seismic load is a part of the load combination. So that can be convenient for properly evaluating your beam for seismic loads according to the building code. Okay, at this point we've gone through all of the primary tabs up here in the data input area, and so what I'd like to do next is move down to the results area and start to work our way through all of the different types of results that are available. To begin with, we'll come to the Calculations tab for results, and that displays this list of horizontal tabs, starting with the Summary Results tab. This one will display the extreme bending stress ratio, indicates the section that's being used to determine that ratio. We can see the moment that's applied, and in this case we can see the design moment, the nominal moment divided by omega. We can see the load combination that produces the extreme bending stress ratio, the span where the extreme bending stress ratio was found to occur, and the location of that maximum within that span. If we come down to the minimum deflection ratios, we have an area that's dedicated to studying live load deflections, so we can see values for the maximum upward and the maximum downward deflections and the ratios that those produce. And then we can see similar values for the total deflection, so maximum upward and maximum downward values and ratios. Moving over to the right hand side, we have the extreme shear stress ratio, again a report of the section that was found to exist at the location where the extreme shear stress ratio occurs. This may seem like a little bit of duplication here, except if we remember the fact that when we come to the beam span data tab, we actually did have the option to specify different sections for different spans. So it is actually important for us to report that section here, because it could potentially be two totally different sections that are found to control here. Continuing down, we have the applied shear and the design shear. We have the load combination that was found to produce the controlling shear stress ratio, the span where the controlling ratio was found to occur, and the location on that span where the extreme shear stress ratio was observed. The last section in the lower right hand corner of the Summary Results tab is the report of the extreme reactions. These are at the service level, reported in units of kips. And here I would point out that we always start with the support number 1, and that always pertains to the left-hand node of span number 1. In this case, that's an unsupported node, and that's why we don't see any values reported here for support number 1, because support number 1 can actually be thought of as node number 1, and it's an unsupported node. But from here we can see that we have two more values reported, supports number 2 and 3, and we can see service level extreme reactions that are found to occur at each of those nodes. Next we'll move over to the Maximum Combinations tab. On this tab we can see that we have a breakdown of values for each of the load combinations that's run, and in fact we also have within each load combination we have design segments. Notice that we have a few design segments that all indicate span number 1. This relates back to the choice that I made for span number 1 to be braced at the 5th point when we were on the beam span data tab. So we have a few design segments here with their segment length indicated, and then the maximum stress ratios for moment and shear are reported. The summary of moment values indicates the extreme positive and extreme negative moment that was found to occur on that design segment. The extreme absolute value of those two is reported here in the MA max column. Then we have the MN value, the nominal strength, and the nominal strength divided by omega, so the design strength. The value of CB, the value of RM for the particular section that we've used. And then we move on into shear values, and we can see the maximum applied shear, Vn, the nominal shear strength, and then the design shear strength, Vn divided by omega. So we can look at these on a load combination by load combination basis, and then further we can break down into span by span, and then even further than that look at a particular design segment within the named span. So that information is presented on the Maximum Combinations tab. Moving onward, the next tab is the MVD Summary tab, where we have two different sub-tabs available. The first one is the ASD service stress combinations, where on a load combination by load combination basis we can see shears and moments and unsupported lengths or unbraced lengths reported at very small increments all along the span. And if I was to scroll down, we would move from span 1, which should end at the 6-foot mark. We move on to span 2, and we continue making slices through span 2, reporting shears and moments and unbraced lengths. And then eventually we would get to span 3. And then at the bottom of the span 3 information, we would move into the next load combination. On the service load deflections tab, we see on a load condition by load condition basis deflections and ratios and effective moments of inertia reported at those small slices all along the length of the beam. Notice that there's a compress incremental results button over here, which can be convenient if you've drilled into a particular loading condition and you've scrolled way down. You can just compress them all quickly to get back to the default view here. The next tab is support reactions. And on the support reactions tab, we can see on a load condition by load condition basis the reactions reported at the various supports. And again, I would make the comment that think of support number 1 as being the node at the left end of span number 1. So in our particular model, that's an unsupported node, and therefore we don't see a support force or a reaction indicated there. But we do see values reported for supports number 2 and 3. So that's a look at everything that we have available to us on the Calculations tab. Next, what I'll do is move down to the Sketch tab, and here we see a graphical depiction of the beam that we've created with its span lengths and steel section designations, and we see a graphical representation of the loads that we've applied to the beam system. And then finally, if I move down to the Diagram tab, we can choose between moment diagrams, shear diagrams, or deflected shape diagrams. Once we make a choice, we can choose whether we want to see a graph that shows all load combinations at once superimposed on each other, or if we deselect that option, then we can use the display load combination drop down to choose a particular load combination of interest, and then look at the shape and the magnitudes. Just keep in mind that the shape in this case, whether I look at dead or if I look at live, or dead and live for that matter, the shape is exactly the same, so it can be a little deceiving because it seems to imply that nothing's changing, but in reality what's changing is the scale over here on the left and the magnitude of those moments. So notice that the maximum value is indicated as 17 when I look at dead plus live, but when I just choose dead, notice that it changes down to 9. So it is definitely reflecting the selected load combination. Finally, I'll point out that if you hover your cursor over the icon over here to the right, you can get an enlarged view for a little bit better detail of the selected graph. So hopefully that's been a helpful look at the steel beam module from the modeling process through configuring the model with the proper settings, loading the model, establishing load combinations to run, and then looking down through the results and interpreting those results and understanding what's available for viewing on the screen. The last items that I'll close out with are to point out that when we are looking at the calculations tab, notice that we do have an indicator over here that indicates that the design is meeting all of our established criteria based on everything that we've selected. And then finally, I'd point out that we have the option to print a report, and so we could come up to the print preview button and take a look at the report and see what would be printed. We can also configure that report by using this properties icon to choose exactly what things would be included in that printed report, and then we have the option to either send that report directly to the printer, or we can choose to create a PDF file of that report and then file that away electronically. So with that, we'll wrap this video up. Hopefully it's been helpful, and please take a look at some of the other videos for the beams of other materials and onward to columns and so on and so forth. Thanks very much. Take care and have a great day.